Hi, this short video is about muons, their basic properties, the decay products and why they might be useful. Muons are leptons, like electrons, with the same negative charge but with a much greater mass. And like the electron, they can occur as antiparticles, in other words with a positive charge. To compare the mass to an electron, we can use a magnetic field, shown here going straight into the screen. An electron will be deflected by this magnetic field, like this. Whilst in the field, the electron will experience a constant force, perpendicular to its path. The path, therefore, is going to be part of a circle. Having a mass 200 times greater, muons travelling at about the same speed are deflected in the same direction, but much less. Unlike the electron, muons are unstable, with a half-life of around 2.2 microseconds. They decay via the weak interaction. In the most common mode of decay, one of the products will be a muon-style neutrino, but because lepton numbers must be conserved, there must also be an electron-style antineutrino, as well as an electron. Muons can be produced in a particle accelerator, but they're also produced naturally, for example as cosmic rays strike the upper atmosphere. A variety of particles are produced, but amongst them muons, which travel at a very high speed towards the ground, typically over 99% of the speed of light. This fact led to some very important scientific observations. If the number of muons arriving at, say, 2,000 meters above the ground is measured, and then that is compared to the number of muons which actually arrive at the ground, you would expect there to be a large difference. At speeds approaching that of light, 2,000 meters would take about 6.7 microseconds. When at rest relative to the observer, the half-life of a muon is about 1.5 microseconds. So that distance of 6.7 microseconds represents over 4 half-lives, which would reduce the numbers to less than a 16th of the original. But that doesn't happen. In fact, the numbers only fall by about 1/2. So why is that? Well, this is the classic experiment which helped to confirm Einstein's theory of special relativity. There are a couple of ways of explaining this. To an observer on the ground, looking at a clock travelling along with a muon, that clock would seem to be running slowly. That is time dilation. From a different point of view, if an observer was sitting on the muon, ridiculous though that seems to be, the ground would seem to be rushing up towards them, and the distance to the ground would seem to be a lot shorter. That is length contraction. One other application I'll mention is, like X-rays, muons can be used to take shadow pictures of solid objects. Because of their huge penetrating power, they can be used to study the insides of very large and very dense materials, and interestingly, even the insides of volcanoes, and therefore might be used to help to predict when a volcano could erupt. Thank you for watching.